Alright, let's continue. Let me open the table of content first. Okay. We are still in chapter 22 here, beyond physical memory policies. Still on homework simulation. Let me open that chapter. I think this one. Okay. Beyond physical memory policies on homework simulation. Okay, let me check. We already take a look at this question, right? And now we will take a look at this. For a case of size 5, generate worst case address reference stream for each of the following policies: first in, first out, least recently used, and most recently used. And the worst case reference stream caused the most miss possible. For the worst case stream, how much bigger of a case is needed to improve performance dramatically and approach OPT? Well, I'm not sure where the closing bracket in here should be. Maybe this one? Just a little nitpick, I guess. Anyway, we had to take a look at the worst case address reference for first in, first out with a case size of 5, and well, the address reference, I think 10. Let me check. Yeah, I think it is 10. Okay, 10. Alright. Let me... what is it called? I guess generate... for the least recently used, the worst case address reference. For the least recently used. Okay, let's see. Okay, right. Case size of 5. Case date. What is it called? 5 page. Least recently used policy. Okay, fill up the case here. Alright. Fill up the case, and then least recently used, right? Okay, if I do this, should I do the same thing? I mean, maybe I can use the same address sequence here. Let's check that out. Beyond, okay. Case size 5. Address this one. Alright, let's calculate this. Okay, yeah. Oh wait, no, this is that is the first in first out policy, not the LRU. Okay. Oh, okay, mid. Kind of the same, I guess. Basically, like the looping. What is it called? The looping workflow, maybe something like that. Yeah, looping sequential workload, I mean. See, when we are trying to access, what is it called? Page 50, right? We will hit 0% hit rate because the previous page is already removed from the cache. So yeah, something like that. Basically, this is my inspiration. Looping sequential workload. And well, the LRU and FIFO policy perform worse here, right? Okay, can also put this in here, I guess. And yeah, even the sequence kind of the same, right? Similar. Oh, wait. Why is this MRU? Is it really? Hold on a minute. Why is this MRU? MRU replace? What? I didn't notice that previously. Yeah, I didn't notice this previously. Oh, interesting. Most recently used replace. Isn't that supposed to be? Oh, that was in replace. Okay, well, maybe that's correct. If I use this, oh, interesting. This is called MRU. This is MRU. All right. Let's change this to LRU is recently used, and if you use MRU, I don't think there's gonna be the words address sequence most recently used, right? So I assume with the MRU policy here, we replace this one, the most recently used. So maybe instead of using, yeah, maybe not something like this. Maybe going backward, right? 0, 1, 2, 3, 5, maybe something like this. Maybe. Let me check. Right. Okay. And then are we just gonna replacing this one? If I try to access, yeah, that make me wonder if I try to access something like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Interesting. So we are only replacing the right side, the most recently used, I guess, and not even considering this one. That is interesting. Okay, so looks like we found the worst scenario with the most recently used that miss all the address access, I guess. 9. Again, this question specified the most miss possible, right? And the most miss possible that I can think of is that we miss every address access. Right? So there is that. But yeah, I'm not sure if this is a valid answer, I guess. We will see. Okay, 5. Okay, something like this. Wait a minute. Okay. Yeah, let's do this, I guess. 4, 5, 6, 7, 8, 9, 10. Okay. Yep. Guess this one. Then best access. Okay, for the worst case reference stream, how much bigger of a case? Oh, hello, Action Pastor. Welcome. We are currently learning about operating system by reading this book. Let me copy this in the chat, or you can take a look at the description. There are some resource there, some learning resource in the description. And now we take a look at chapter 22, Beyond Physical Memory Policies, basically, what is it called? Basically, the policy that we use to decide which memory being replaced, something like that. And there is the first in, first out, is recently used, and other policies, I guess. And now we are taking a look at the homework simulation to understand what is it called? To understand about the batch replacement policy or the memory replacement policy that available, I guess, in the simulation, which, if I remember correctly, there are quite a few. First in, first out, list recently used, optimal and unoptimal, and then there is also random policy, and then also clock algorithm, and the policy that is not written in here but also available is the MRU, the most recently used policy, something like that. And now we are taking a look at question 2, basically trying to generate, or what is it called? Trying to, well, yeah, let's call this generate, I guess. Trying to generate the worst case address reference for each of the following policy: the first in, first out, least recently used, and most recently used. And there's this information: worst case reference stream cause the most miss possible. And I assume if we miss the address reference, that also considered to be the most miss possible. So that's what I did here. Basically, from this 10 address access or reference, we miss every address. Miss 10 here. And the hit rate is 0%. Okay. So yeah, that is that. Now let me take a look at this. For the worst case reference stream, how much bigger of a case is needed to improve performance dramatically and approach OPT? And approach OPT, huh? So I assume we need to know what is the result of OPT, right? Even though OPT is missed. Even though OPT also miss all the address access. Okay. That is interesting. Wait. Alright, let me try this. The worst case scenario for first in, first out policy, but we are using the, what is it called? The optimal policy here, basically trying to replace the furthest memory that we are not going to access in the future. Okay. For this case, hit 4. Alright. Okay. How many keys do we need? Maybe 6 for the first in first out to be close to the optimal, what is it called, optimal policy. Okay, yeah, hit rate 40%, miss 6 and hit 4, similar to this one when we are using the optimal policy. Okay, we are just increasing what is it called, the case size by 1, and we can get the same performance, I guess, as the optimal policy. Okay, and then for the LRU, let me check. LRU, I guess the same too. Okay, hit 4, miss 6, so we have 40% hit rate, something like that. Now I mean, I'm not sure if the worst case address reference here need to be the same across this policy, Basically, we use the same address reference for first in first out policy here, and least recently used, and also most recently used. If we are using the same address reference, then maybe only increasing 1 case to make 1 case size to make the performance similar to the optimal solution. Maybe I mean, if we need to use the same address sequence or memory reference stream across 3 different policy here, then the MRU policy, the most recently used policy, having the same what is it called, having the same performance, I guess, as the optimal policy here, this one and this one. So yeah, I'm not really sure what do we need, the same stream or not across these 3 policy. I assume it is not. I mean, we can have different kind of address reference stream or address sequence, I guess. But yeah, the interesting one is in this address reference stream for the, what is it called? For the optimal solution. Because the optimal solution itself also miss everything. with the hit rate 0%. Okay, that kind of tricky. If I increase this to 6, still miss. Do I need to increase this to 9 maybe? Interesting. Zero, okay. I mean, yeah. We didn't try to access the same memory, right? So that's why we miss a lot of things. We miss everything, I mean. So maybe this is the worst case for every policy. Yeah, let's not use this one. How do I? How do I decide which scenario that the MRU or the most recently used policy is worse without actually being worse for every policy, right? Okay. But I need to replace the last one, right? Maybe if I do this 4 and then 5 and then 4 again and then 5 again, maybe constantly going back and forth here. Let me try. I mean 4, 5, 4, 5. Okay. Alright. Okay. Then miss. But what about the optimal solution? The optimal solution or policy, I guess. Okay, now we are talking. Alright, see, it is the same, right? 4 hit, 6 miss, hit rate 40%. Okay, let's change that. 4, 5, 4, 5. So this become 4, 5. Something like this. MRU, then miss here with the hit rate 0%, something like that. And now let's try increasing the case by 1. Alright, so yeah, as a comparison, this is the statistic for optimal policy for hit. 6 miss, right? With the hit rate 40%, with the case size of 5, and this is the MRE policy, the same address sequence or address reference stream, but we need to increase the case size to 6 to have the statistic similar to the optimal solution, which is 4 hit, 6 miss, and 40% hit rate. Something like that. Okay. Well, of course, this is assuming that what is it called? We only have 10 address reference stream, right? If we have more, then we might need to change that. Okay. How much figure of a case is needed to improve performance dramatically and approach OPT? Yeah, in my solution here, we only need to increase the case by 1. Okay. Alright. Generate a random trace. Okay, question 3. Here, let's continue. Generate a random trace that is use Python and write a script that outputs random address, which you can then feed into the simulator. Okay. How would you expect the different policies to perform on such a trace? Output random address. Basically, what is it called? Basically, a random number is that it? And then feed that into the simulator with the test A flag or the address flag, I guess. Well, maybe we can use the address flag or the address file flag. So we are saving this random number in the file, I guess. Maybe. How would you expect the different policies to perform on such a trace? Now generate a trace with some locality. Okay, wait a minute. So I need to generate the random number. How would you expect the different policies to perform on such a trace? Well, if it is random, then I guess depend on the address, depend on the luck, I guess. Maybe something like that. What algorithm is it? Is it related to case management of operating system? Yes, I guess. This is related to the case, or maybe to be precise, the memory management of the operating system. Yeah, this one, the policy for the, what is it called? memory replacement, something like that. So basically deciding which memory to replace in the operating system. Okay. Yeah, I guess I will skip this. Now let's continue to this. Now generate a trace with some locality. How can you generate such a trace? Yeah. Oh. I assume the locality in here means something like spatial locality n. So on, where is it? Okay, this one, right? Spatial locality, and then temporal locality, the principle of locality. And spatial locality basically means you're accessing the page or the memory around it. Temporal locality is what is it called? Accessing the memory that recently accessed, maybe something like that, that have been accessed in the near past and likely to be accessed again in near future. Maybe something like that. Okay, so this is interesting. With some locality, how can you generate such a trace? Okay, how much better than random is the is recently used? How does the clock algorithm do? Okay, how about clock with different number of clock feet? Okay, this is interesting. Let's try this, I guess. How can you generate such a trace? So basically, if I understand correctly, generate the trace with specification what is it called? Using the address around it, and also using the recently address for the temporal locality, I guess. I mean, if I generate that manually, maybe it would be something like this. I mean, depends on the case, right? If you are using the case size 3, if you are using the case size 3, maybe we can do something like this. I'm not sure if this is correct or not. How many is this? Okay. And maybe 0, I guess. assume we only have 3 miss here. Let's try that out. Are you? We are using the default case size. It is 3 here. Okay. I'm not sure if that is correct or not, but let's find out, I guess. Okay. See, miss 3 and then 7 hit. Okay. We are using, I assume, some kind of locality. But yeah, I'm not sure yet. How much better than random? Okay, let's try random. Yeah, for the comparison, I guess. Okay. In this sequence, it's the same. It is kind of interesting. Let me check the trace. Alright. We are not replacing any case here. Okay. Maybe this is not correct. Maybe something like this. At some locality, huh? Around it, right? And then, let me think. Around it. If we only have 3 cat size, yeah, this keep changing. But the random one is not. Okay, maybe I need to replace. Okay. 1, 2, 3. And then accessing accessing 2 maybe, accessing 1, accessing 3. Okay, and then this one accessing 0, 2, and then 3. Maybe the last one is accessing 2 again. I'm not sure if this is correct. Let's check that out. Okay, this is this recently used. What about the the same. Okay. Yeah. Why are you studying? I'm just curious. Because I'm curious, I guess. That's why I'm studying. Yeah. Okay, I'm a developer. I study temporal already, but just the theory. Never did operating system development. Looks complex. Also, how will you give reasoning on how an algorithm is performing better than the other? I'm still not sure what is it called? How to decide what algorithm is performing better than the other? I mean, it depends on the metrics, right? That's why we have a lot of algorithm and we need to choose the algorithm that fit the specific scenario. So basically, there's a saying or statement, one size fits all, fit nothing. So there is no one algorithm to rule them all. So we need to, what is it called? We need to use the optimal algorithm depending on the goal that we want to achieve. Or we want fast performance, for example, or we want what is it called? Less storage space, fast performance, or less storage space. Yeah, depending on the goal, there's always trade-off. There is always trade-off with each algorithm, as far as I know. So we just need to decide what kind of trade-off we are willing to make. So yeah, that's, I guess, the reason to check which algorithm to use, which trade-off we are willing to make. Okay, I'm still not sure about this locality stuff. How to generate a trace with some locality. Okay, well, let's try this first, I guess. I will take a look at this off stream maybe, but I'm not sure if I will find the answer. Okay, use a program like Valgrind to instrument a real application and generate a virtual page reference stream. For example, running Valgrind. Okay. Test tool, make it trace mem, yes. Okay, ls. Oh, we are using the ls program here. Will output a nearly complete reference trace of every instruction of data reference made by the program ls, right? Let me check. I think I already have Valgrind installed, right? So there is that. The tool. Let me check the manual page. Okay, I guess this one. Run Valgrind tool called tool name. For example, memcheck gets grind. Oh, there's also called grind. Hell, grind. What is that? Okay. VLT mas if t hat leaky non exp ppv what etc. And the default is memcheck. Okay, so if we didn't provide the flag tool here, we will use the memcheck tool, I guess. And this one leaky. What is the leaky tool? Is there any leaky? Okay, leaky option. When enable, leaky prints the following statistic. Trace mem, yes. Oh, this one. Okay. When enable, so I assume the trace mem here specific to leaky tool, maybe. Let me check. Oh, here, maybe the trace mem here specific to the leaky tool. Okay, when enable, leaky prints the size on address of almost every memory access made by the program. See the comments at the top of the file. Okay, leaky/lk main, leaky/lk underscore main.c for the tell about the output format, how it works, and inaccuracy in the address trace. Note that this option produces immense amount of output. Okay, interesting. So we are using the leaky tool in the file grind tool chain, I guess, and using the option trace mem for the leaky tool, and running that with ls program. This one. Let me check. Tool leaky trace mem, yes. Is it gonna be? Let me check on another screen first. Just make sure. Nothing sensitive is there. Tool leaky trace mem, yes, ls. Okay. Okay. There is a lot of output. Let me show you, I guess. For grind, not that one. What is it? Tool leaky trace mem, yes. Yeah, there's a lot. Okay. Nearly complete reference trace of every instruction and data reference method made by the program ls. To make this useful for the simulator above, you have to first transform its virtual memory reference into a virtual page reference virtual page reference, then by masking off the offset and shifting the resulting bit downward. I guess this means we need to right shift to get the virtual page number reference from the memory reference. How big of a case is? How big of a case is needed for your application test in order to satisfy a large fraction of requests? Plot the graph of each working set as the size of the case increase. Okay. Let's try maybe something like this. No, not that one. Maybe something like this. How do we read this information? To make this useful for the simulator above, first transform each virtual memory reference into a virtual page number reference. Okay. You know what? Let's take a look at this on the next session. I assume. Yeah, what is E? The E here. And what is L? Is it the leaf function? And what is S? I need to understand that. Alright, let's continue this on the next session, exploring the Valgrind, I guess. So that's it for now. Thank you for watching and see you next time. Bye bye.